Your wall outlet gives you 220 volts, but the power lines outside your home carry 400,000 volts. Why such an insane number? Why not just send 220 volts directly to your house and keep things simple? The answer is going to change how you see electricity forever. The electricity in your phone charger is 5 volts. The electricity in power lines can reach 400,000 volts. That's an 80,000x difference. Why? Because if we use 220 volts to transmit power, your electricity bill would be 10x higher and half the world would be in the dark. Here's the short answer. When you send electricity through a wire, some of it gets lost as heat. The more current flowing through that wire, the more heat you lose. But here's the trick. If you increase the voltage, you can deliver the same amount of power with less current. Less current means less heat. Less heat means less wasted energy. That's it. That's the whole secret. Now let me show you the math behind it, because the numbers are actually shocking. Let's say you need to deliver 1 megawatt of power to a city 100 kilometers away. If you try to send it at 220 volts, you'd need over 4,500 amps of current flowing through those wires. 4,500 amps. Do you know what happens to a wire carrying 4,500 amps? It melts. Actually, it doesn't just melt, it vaporizes. The power loss in a wire follows a simple formula, P times I² times R. That I² is the killer. If you double the current, you don't double the losses, you quadruple them. So at 4,500 amps, even a thick copper wire would lose most of your power as heat before it ever reached the city. You'd be paying for electricity that literally disappears into thin air. And this isn't theory. This is exactly what happened in the 1880s. When Thomas Edison built his first power grid in New York in 1882, he used low-voltage DC, direct current, and it worked. If you lived within 1 mile of the power station, that's it, 1 mile. Beyond that, the voltage dropped so much that the lights wouldn't even turn on. Edison had to build a power station every mile or two. That's insanely expensive. Then Nikola Tesla and George Westinghouse said, what if we change the voltage? Use extremely high voltage for transmission, then step it down near the customer's home. That requires a device called a transformer. And here's the thing. Transformers only work with AC, alternating current. They cannot work with DC. This single fact is why the entire world runs on AC power today. Alright, let's make this crystal clear with real numbers. Say a power plant generates 500 megawatts. Option 1. Transmit at 22,000 volts. Current needed is about 22,700 amps. Power lost in the line equals I² times R. Roughly 257 megawatts lost as heat. That's more than half your power gone. Gone. Just heat in the air. Option 2. Transmit at 400,000 volts. Current needed is only 1,250 amps. Power lost? Roughly 0.78 megawatts. That's not a small improvement. That's going from losing over half your power to losing less than 0.2%. It's not overkill, it's survival. But wait, if 400,000 volts is so efficient, why not go even higher? Why stop there? Great question. The answer is insulation. At 400,000 volts, air itself starts to conduct electricity. You need towers that are 30 meters tall just to keep the wires far enough from the ground. The insulators hanging from those towers are massive. Each one is over 2 meters long. Go much higher and you'd need towers the size of skyscrapers. The cost of the infrastructure starts to cancel out the efficiency gains. So 400 to 800 kV is the practical sweet spot. So here's the complete journey. The power plant generates electricity at around 20,000 volts. A step-up transformer immediately raises that to 400,000 volts. It travels hundreds of kilometers on those massive tower lines you see along highways. At a substation near your city, a step-down transformer drops it to about 11,000 volts. Then a smaller transformer on the pole outside your house brings it down to 220 volts. Every single step exists for one reason: to minimize the current and therefore minimize the loss. If this kind of breakdown helps you understand power engineering better, hit subscribe. I'm building this channel to explain the stuff your professors skip, the real-world why behind every number. New video every week. Now, here is something that might surprise you. Remember how I said Edison's DC system failed because you couldn't change its voltage? Well, modern technology found a workaround. It's called HVDC, High Voltage Direct Current. Today, some of the longest power lines in the world actually use DC, not AC. Undersea cables, lines over 800 kilometers, and connections between different grid frequencies all use HVDC. It turns out Edison wasn't entirely wrong. He was just 130 years too early. But that's a story for another video. What topic should I break down next? Drop it in the comments. So next time someone asks why power lines carry 400,000 volts, you know the answer. It's not because we like danger. It's because physics leaves us no choice. Higher voltage means lower current. Lower current means less loss. Less loss means electricity actually arrives at your home. It's that simple and that elegant. And if you learned something new today, subscribe. I'll see you in the next one.